Once again, okay. This is the 37th lecture on small signal amplifiers and feedback. In the last lecture, I had introduced the terms Ft and F beta for the figure of merit of a transistor, and I explained that if you measure beta, that is the short circuit current amplification factor of a transistor, then beta varies with frequency, and the variation is like this. That is, at low frequencies and at midband, beta is a constant. Kajal, can you give this to two boys? Beta is a constant at beta 0, and then at some frequency f beta, the value becomes beta 0 by root 2. And this is called the beta cutoff frequency, and the frequency at which the value of beta becomes equal to 1 is the so-called transition frequency, or f sub t. The variation of beta determines f beta and f t and the relationship between f t and f beta is that f t is equal to beta 0 times f beta, and that is why f t is also sometimes called the gain bandwidth product. As an example of this, suppose the manufacturer specifies this in a clever way. He doesn't give he doesn't give the value of C pi. What he does is he gives either the value of f t or the value of f beta, one of them, all right, and also beta 0. Then you know that, is that enough for specifying a transistor f beta and f t? F beta, as you know, is 1 over 2 pi r pi C pi. So it is not enough to specify f beta and beta, r pi must also be specified, or you must find out r pi. How do you do that? If the capital I sub C, the DC collector current, is known, then you find GM as 40 IC, and from this and beta 0 you find r pi, and if you know r pi and beta, f beta, then you know C pi. As an example, for 2N3114 transistor, the manufacturers have specified that a typical operating point r pi is 1500 ohms. Beta 0 is 50, beta is at 50 at 1 kilohertz and is 2.7 at 20 megahertz. This is all that is specified. R pi is given, the values of beta at 2 frequencies are given, and you are required to find out f t, f beta and r pi, no, and C pi. This is what is to be found out. Common sense says that 1 kilohertz is a sufficiently low frequency, and therefore you can take beta 0 as equal to 50, all right. Beta 0 is equal to 50, and you know that the variation of beta is given by beta 0 1 plus j f by f beta. This is the variation, and we have been given that the magnitude beta, which is beta 0 divided by square root of 1 plus f by f beta whole squared, this is given as 2.7 when frequency is 20 megahertz, f is 20 megahertz, all right, and therefore 2.7 is equal to 50 beta 0 divided by square root of 1 plus f by f beta whole squared. Now, at such a high frequency 20 megahertz, 1 can be ignored compared to f by f beta, all right. From 50 beta has come down to 2.7, it is beyond f beta, and therefore f by f beta whole squared term dominates the denominator expression, and therefore you can write 2.7 as equal to 50 divided by, well, f by f beta, and f is 2.7 megahertz, and therefore f beta is equal to 20. Therefore, it is 2.7 multiplied by 20 divided by 50 megahertz, and this is equal to 1.08 megahertz. This is your f beta, and you know, if you know f beta, then you can find out c pi. F beta after all is 2 pi times r pi is 1500 and c pi. Therefore, c pi is equal to 1 over 2 pi 1500 multiplied by 1.08 times 10 to the 6, and this calculates out to approximately 98 puffs, 98 picofarads. That is how one finds c pi. C pi is never specified by the manufacturers. All right. Actually, it is c pi plus c mu, but c mu is of the order of a few puffs, 2 or 3 puffs. So we take everything as c pi. We ignored that quantity. All right. And if we know f beta, then of course we know f t also. F t is 50 times f beta, that is 1.08 megahertz, which is equal to 54 megahertz. All right. So, you should be able to calculate the quantity of interest given all other quantities. We next consider what happens when one amplifier stage is cascaded to another. If the amplification transistor stage 1, transistor stage 2, if the amplification provided by one stage is not enough, then you cascade 2 stages. Normally, it looks like if A1 is the gain of the first stage and A2 is the gain of the second stage, then the overall gain should be A1, A2, except for the fact that the 2 stages usually in a BJT amplifier are interactive. In other words, the load of this stage, if you consider the load of the first stage as the input of the second stage, then you shall be right in calculating A1 and A2. But if you calculate A1 by open circuiting this, all right, open circuit voltage divided by this, then A1, A2 formula shall not be valid, because if you look back here, transistor stage 2 is being driven by A1, let us say if this is Vi, A1 Vi, the Thevenin source in series with whatever you look back, the Thevenin output resistance, let us say RT, and therefore what is applied here is not A1 Vi, but it is reduced. There will be a potential division between RT and perhaps R pi if it is a common emitter transistor, and therefore in calculating the gain of cascaded stages one has to be particularly careful, and we shall take a fairly elaborate example to illustrate this. Let us consider a 2-stage amplifier. Please try to draw with me. A 2-stage amplifier, I will draw the complete circuit. RS, then you have a coupling capacitor, biasing resistances R1 and R2 plus VCC, then the transistor there is an RE and C sub E, this connects to the base. This is the first stage, is coupled to the next stage. Oh, there is a resistance here, R sub C, the collector resistance of the first stage. Then it is coupled to the second stage by a capacitor R2. Let us say they are identical stages, R2, R1. Then you have the base. We do not use an extra load here because the second transistor acts as a load to the first transistor, all right. And then there is a resistance here shunted by a capacitance, and there is another resistance here R sub C. Finally, you have a coupling capacitor and the load RL. This is a typical two-stage RC coupled amplifier. Let us say the root mean squared value of the voltage here is V0, all right. Now, we have to calculate the gain of this stage. Whenever no specifications are made with regard to frequency, it is implied that it is the mid band gain, and at mid band by definition this is a short, this capacitor is a short, this is a short, this capacitor is a short, this capacitor is a short, and this is a short at mid band, all right. Also the transistors Q1 and Q2, their internal capacitances are open, C pi and C mu. Let us say that the two transistors are identical, Q1 is identical to Q2 and suppose R sub C is equal to R sub L, R sub C, R sub C, R sub L, they are each 6K, all right. R1 parallel R2, that is RB, RB is so chosen that it is much greater than R pi, and R pi is 1K, which is also equal to Rs, all right. This resistance and R pi, they are identical for simplicity. And we are also given that GM at the operating point of either transistor is 100 millimho. 100 millimho means 0.1 mho, isn't that right? 100 times 10 to the minus 2. So this is the data that is given. Beta is not given, we do not need it. How much is beta for this transistor? Pardon me? 1K multiplied by 0.1, so 100, isn't that right? Beta is 100. Let us draw the equivalent circuit and see if we can calculate. You will see that if you take care in drawing the equivalent circuit, then analysis is almost by inspection. There is nothing, no equations had to be written. Now, let me go ahead with the equivalent circuit. Vs, then you have Rs. We have ignored R1 parallel R2, and therefore it is simply R pi. R pi, and if we call this voltage as V1, then the output of the collector is GM V1, and its load is, there are two loads, one is R sub C and the other is R pi of the next stage, all right. The load of this transistor is R sub C, and then whatever it sees R1 parallel R2, which we ignore, and from here to ground there shall be an R pi, and therefore there is an R pi, and let us say this is V2. Then at the output of the second transistor we shall have GM V2, and what about the load? Load shall be RC parallel RL, isn't that right? It shall be RC parallel RL. So let us call this R0, RC parallel RL, and this is V0. And the calculation of voltage gain is very easy now. V0 by Vs is the voltage gain, and we calculate this in 3 steps: V0 by V2, then V2 by V1, and then finally V1 divided by Vs. All right. We calculate this in 3 steps, and it is quite clear that V0 by V2 is simply minus Gm times R naught. This is minus Gm times R naught. V2 by V1 shall be minus Gm times the parallel combination of Rc and R pi. All right, Rc and R pi. And V1 by Vs will be simply R pi divided by R pi plus Rs. And if you substitute the values and carry out the algebra, my calculator gave S of V. You just have to substitute the values now. Everything is known, all right. And if you calculate this out, you notice that the gain is positive because it is a two-stage amplifier. First stage gives it an out of phase output voltage. Second stage gives out of phase with out of phase. Two negatives make positive, and therefore the output voltage shall be in phase with the input voltage, and the value that calculates out is 12,857, which is a fairly large number. This is the mid band gain of these two transistors. We have not asked for very sophisticated transistors. They are commonly available, beta equal to 100. That is not a very large beta transistor. All right. Now such a large number usually, as you know, is expressed in decibels, gain in decibels. If you want to express in decibels, then you should take 20 log 10 of this number, and I leave it to you to calculate how many decibels shall this be. How many decibels? What is your guess? This is more than 10 to the power 4, and therefore it is more than 80 dB. Okay, that is how usually engineers, electrical engineers, express the gain. There are the exercise for determining the low frequency cutoff and high frequency cutoff for cascaded amplifiers can be quite tough, but I am sure if you take help of C.J. Miller and the tricks that some of them which we disclosed in the earlier class and some in the tutorial class, you should be able to do that. So we leave other problems for the tutorial class, and we consider the question of feedback in amplifiers. Feedback in amplifiers. The definition of the term feedback is that it is a phenomenon in which the output influences the input. If a part of the output is utilized to influence the actual input to the amplifier, then we say feedback exists. For example, common example is the op amp. As you know, in the op amp, the gain, the open loop gain is very large, tends to infinity, and if you wanted to make a non-inverting amplifier, then what you do is you use a resistance here and a resistance here. So what is being actually done is that the input Vi, the actual input to the amplifier is Vi minus, if this is R2 and this is R1, the actual input to the amplifier between these 2 points is Vi minus V0 R1 divided by R1 plus R2. Is that clear? This is the actual input, and therefore the input that is applied to the amplifier is being modified by the output. A part of the output is being fed back to the input, and this multiplied by A is equal to V0. And the kind of feedback that exists here is negative feedback, because the actual voltage applied to the input of the op amp is less than what is actually applied. All right. If the input had increased, then we would have said positive feedback. So this is negative feedback. Okay. The evaluation of W110N to the teacher can either be positive or negative depending on how the teacher was. If I take a general philosophical attitude, well, I say that I can represent feedback schematically like this. I have an input, let's say Vs, a source, and an amplifier of gain G, whose output is V0. A part of the output, this is called a block diagram. I am not showing the actual circuit, I am showing the relevant signal quantities and the amplifier in terms of a gain, in terms of a block, just a rectangular block. A part of the output or the output is fed to another circuit which we call the H circuit or the feedback circuit, and this output, which is obviously V0 times H, all right, is used to influence the input. That is, what we do is we simply add the two inputs, we simply add them in a block called a summer. All right, we add Vs and V0H, and this is the actual input to the amplifier. Before Vs comes to the amplifier, we do something, we mix it with a part of the output, and this is called a feedback circuit. This loop is called a feedback loop, and it is very easy to calculate what the gain is under the condition of feedback. Under the condition of feedback, we represent the gain by Gf, and you see Gf will be simply V0 divided by Vs. All right, but as you can see from this, Vi is equal to Vs plus V0 H. All right, Vi is equal to Vs plus V0 H, and Vi times G is V0. Therefore, this is V0 by G. Is this clear? This voltage, this signal is Vs plus V0H, and this signal when multiplies G shall give V0. Therefore, this signal must be V0 by G. Okay. Now, if I manipulate this, then you see Vs times G, GVs plus GH V0 is equal to V0, and therefore V0 by Vs shall be simply GVs divided by 1 minus G times H. No Vs shall be there. Okay. It is simply G by 1 minus GH. If H is 0, that is, there is no feedback, then the gain is simply equal to G. Okay. So, for a feedback amplifier or any feedback system, the gain is in general given by 1 minus GH, where G is called the forward path. G is called the forward path, the signal travels in the forward direction. H is called the reverse path or the feedback path. It is this path through which feedback is applied. All right, G, H, and the total loop is called the feedback loop. And you can see that G times H, this quantity figures here, G times H is the gain from here to here. If you start from this point and you come here, the gain is G times H. All right, it is also called the loop gain. G times H is called the loop gain. It is the gain of the feedback loop. That is, if you start from a point in the feedback loop and try to come back to the same point through the summa, then the overall gain from here to here is GH, the loop gain. Now, the quantity GH affects the overall gain very drastically, very substantially. For example, suppose G and H are real quantities, and suppose H is negative. Let us say H is less than 0, all right. G can be positive, or no, I am sorry. Suppose GH is less than 0, the product GH is less than 0. Then obviously, if G and H are real, then obviously GF shall be less than G, and the feedback shall be negative feedback, because the gain is reduced, all right. On the other hand, if GH is greater than 0, and let us say less than 1, all right, then GF obviously is greater than G, and the feedback is positive feedback, all right. So, feedback can be positive or negative. Do we use positive feedback? Yes, we do use. We use negative feedback also. Now, as an example of positive feedback, let us look at a typical circuit. Let us look at a transistor amplifier in which the load is a tuned circuit. The load is a parallel LC circuit. This is plus VCC, L and C, and for simplicity, let us represent the biasing by this Thevenin equivalent circuit, that is RB and VBB, all right. Now, normally what we shall do is we will connect this point to this point. Suppose S is closed, suppose the switch S is closed, then can you tell me what the gain of this circuit versus frequency shall look like? The parallel resonance circuit has the highest impedance at the resonant frequency. What is the resonant frequency? 1 by 2 pi square root LC. At this frequency, the load has the highest value. Ideally, it should be infinity, but because of resistance of the inductance and because of the parallel resistance of the capacitance, this load, effective load at resonance, is less than infinity. But whatever the load is, you know the gain is minus GM times the effective load. So, if we say resonant resistance is R res, then the gain shall be minus GM R resonant at the frequency 1 by 2 pi square root LC. If we go away from resonance, either on the right side or on the left side, the gain shall decrease, and therefore the gain shall follow a resonance curve like this, where the maximum gain shall be minus GM times the resonant impedance, all right. Now, suppose, is this point clear? Instead of a resistance, I have an LC circuit here, and if I have an LC circuit, then the gain shall be maximum at the frequency of resonance, and you know that if we vary the capacitance, then the resonance frequency can be changed, and this is what we do in the input stage of a radio receiver, ordinary radio receiver. We actually vary a capacitor so as to vary the frequency at which the gain is a maximum, and it is this frequency which shall be picked up by your radio, all right. Okay. Now, suppose we use a coil here, use a different color. Suppose we use a coil here, okay, a small coil, maybe 1 or 2 turns, and we connect this coil to these 2 points. Keep the switch S open, all right. We can so orient the winding direction such that a part of the output is fed back to the input. You see, the actual signal at the input between the transistor base and ground shall be the input signal plus the signal that is fed back from the output because of the magnetic coupling between these two inductors, all right, and this is a very practical circuit. You feed back a part of the output, and if the feedback signal helps the input signal, that is, if these two are in phase, Vi and the feedback signal, if they are in phase, if they help each other in the same direction, then what you will get is you will get an enhanced gain, all right, the gain shall increase. On the other hand, if the direction of winding is opposite, that is, if the feedback signal opposes the input signal, then the gain shall be decreased, and it shall be something like this, let us say. So, you can use this, a very simple circuit can be wired up in the laboratory to demonstrate the effect of feedback. Positive feedback increases the gain, negative feedback decreases the gain. I must mention that in order that the frequency of resonance remains the same, the coupling between the two must be loose. If they are brought very close to each other, then the effective inductance that changes because of the mutual inductance. So, it must be kept loose, but it can be very easily demonstrated that if you wind the coil in the reverse direction, then you get negative feedback, lower amount of gain as compared to if you wind the coil in the right direction. Now, let us go back to this expression Gf equal to G by 1 minus Gh. Feedback gain is equal to G by 1 minus Gh. Suppose Gh at some frequency, Gh normally shall be a function of frequency. Here G was a function of frequency, the gain. Without this coil, the gain is a function of frequency, and H could be a constant. H could be a constant. H is the fraction of the output voltage. That will depend on the turns ratio between these two, all right. If this is 10:1, then 1/10 of the voltage would have been fed back to the input, okay. So, G is frequency dependent, H is not. On the other hand, there are systems in which G is frequency independent and H is frequency dependent. In either case, if at some frequency, let us say omega equal to omega 0, if Gh is equal to 1 plus J0, that is, if Gh has a magnitude of 1 and an angle of 0 at some frequency, what do you think shall happen to Gf? It shall go to infinity. Now, what does infinite gain means? That means the amplifier can give an output without an input, which means that the amplifier generates its own input, and this is the condition for oscillation in this circuit. The circuit then oscillates at omega equal to omega 0, oscillates at this particular frequency, and this is how one makes oscillators. For example, yes, in the previous circuit, if feedback is enough, then this circuit shall oscillate. In other words, you shall not require this Vi, this source shall not be required. If you couple an oscilloscope from here, you shall see pure sine waves on the oscilloscope. This is how one generates sinusoidal frequencies. Such an oscillator is called a tuned oscillator, because there is a tuned circuit here, there is a resonant circuit here, all right. A tuned circuit oscillator is not practicable at low frequencies like audio frequency. If you want a 1 kilohertz oscillator, then the values of inductance and capacitance required are very large, and they cannot be obtained from the ready stock in the laboratory. Therefore, what we do is we use alternative means. Let's look at some of the audio oscillator circuits, and let's consider an idealized amplifier. Let us consider an amplifier A, okay, which gives a gain A and a phase angle of pi. For example, a single stage a single stage BJT amplifier gives a gain and a phase shift of 180 degrees. Okay. if this circuit is connected to a circuit like this, 3 RC, 3 capacitors and 3 resistors, capital R, capital R, capital R, then it can be shown that if you feed back the output of this circuit to the input, then the circuit shall oscillate. Now the reason is the following. We have assumed that this amplifier has a gain A and a phase shift of pi, and therefore if you want GH equal to 1 plus J0, G is obviously G is A angle pi. If you want to make GH equal to 1 plus J0, what do you require H to be? H must be equal to 1 by A and angle pi. Alright. This network, this 3-stage CR network can give a gain of 1 by 29, can give a gain of minus 1 by 29 at the frequency which you can analyze. The frequency is given by 1 by root 6 RC. It can be shown by circuit analysis that if you put an input voltage here, the output voltage shall be exactly out of phase at this frequency, and the attenuation is 29, 1 by 29. Therefore, can you tell me what gain shall be needed for the amplifier? 29, right? So an amplifier, if you design for a gain of 29, a single stage amplifier which gives a 180 degree phase shift, then and you connect this, that will be the story. Unfortunately, if you use a single transistor, the output impedance, output resistance of the transistor is not 0. Here we are assuming that the output resistance is 0, the amplifier is ideal, which is not the case. Similarly, the input impedance of the transistor is not infinity, that is capital R is affected, capital R is affected by the input impedance of the transistor. Input impedance of the transistor approximately is R pi, alright. Therefore, the calculation shall be a bit more involved, and the actual circuit of a BJT oscillator, the actual circuit will be like this. You have a BJT, then you have an R sub C, CR, this is the feedback network now, CR, CR, and this goes to, do you need another resistance here? Because you are going to bring this for feedback, you are going to bring this over here. So you don't need another resistor. This resistor could serve the purpose of, alright. If you want for a specified frequency, you might use another resistor, but this may not be needed. Anyway, I will show another resistor here. This is the actual circuit of a BJT, so called phase shift oscillator. Phase shift oscillator. Why is it called a phase shift oscillator? Because the H circuit shifts the phase by 180 degrees. Pardon me? This circuit, this 3-stage CR shifts the phase by 180 degrees. Now if you wish to analyze this circuit, the analysis strategy is the following. Yes. Right. Correct. We can do that, we can do it that way also. If that satisfies Aditya, what we shall do is we will use an R here and a C here. It gives the same result, except that we require an extra capacitor here. Isn't that right? Because otherwise you cannot block out DC. That is why the CR circuit is preferred. This would be a lead circuit, pi 180 degrees leading, isn't that right? Because the CR circuit, the output is leading the input. On the other hand, if it is an RC circuit, the output shall lag the input, and therefore if we take RC, 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 it shall be minus pi. Agreed? Plus pi or minus pi, it does not matter, either way it shall work. But the problem is how to analyze this circuit. What is the frequency of oscillation? Because the amplifier is not ideal. So what we do is like this: we assume that there is a signal source Vi. We assume that there is a signal source Vi, and at the input, then we have the RB, and we have the input impedance of the transistor, that is R pi. Okay. At the output, it is beta. No, let us work in terms of GMV. This is V. V is the same as Vi. All right. I am drawing the equivalent circuit of the single stage BJT phase shift oscillator. I have a GMV, then I have CR. No, not quite. I have an RC. Okay, I forgot about that. I must have an RC here. RC, then CR, and CR. What you want is that this should be coupled. This should be coupled to the input. When can you couple this point to the input for oscillation? When will GH be equal to 10 degree? That means this voltage should be precisely equal to Vi. That is correct, and then you can forget about it. So all that you have to do is analyze this circuit. GMVI, V is equal to Vi, GMVI in parallel with RC, which you can convert to a Thevenin's equivalent, a voltage source in series with a resistance. Then you have a 3-stage ladder network, which you analyze and equate the output to Vi. This will give you the conditions for oscillation, and this condition shall not be exactly 1/29 and 0 degree. It will be affected by RC. All right, it shall be affected by RC, and since this is going back here, you should, in fairness, shunt R by R prime shall be R parallel RB parallel R pi. Is the point clear? No? After all, in an oscillator, you are going to connect this point, to this point, and therefore this R, the last resistance, shall be parallel by RB and R pi, and you have to analyze under that condition. Let us take another case of an oscillator. Is there any question on this? I am not doing the analysis because by this time you should be an expert in circuit analysis. All right. Let us consider another. Let us say we have an op-amp. Now forget about BJT. Let us say we have an op-amp in which has been adjusted for non-inverting gain. This is R1 and this is R2. Okay, and the input is applied here. I want to make this into an oscillator, and one of the ways, you see this block is equivalent to an amplifier of gain 1 plus R2 by R1, and the phase shift is 0 degree because it is non-inverting. What is the input impedance? Input impedance is infinity. What is the output impedance? 0. So it is an ideal amplifier. It is an ideal amplifier. Now I want to make this into an oscillator. So what I do is, this is an alternative circuit. I use an RC. Obviously here G is frequency independent. I use a series RC and a parallel RC. RC and RC. What should be my aim now? This is a 0 degree. So my aim should be to get a 0 degree phase shift from the H network and an attenuation 1 by A. Is that okay? Alright. Then I will connect this to this point. Now by analysis of this network, it can be shown that this happens, that is the gain of this network is exactly 1/3 the gain of this network. If you call this V0 and if you call this Vi, then V0 by Vi is very easy to show. It's a simple potential division. Okay, it can be shown that V0 by Vi is 1/3 0 degree, phase shift is 0 at omega 0 equal to 1 over RC, omega 0 equal to 1 over RC. Alright. No under root. Under root in the case of LC circuits. In the case of RC circuits, no under root. Alright. Omega 0 is simply the inverse of the time constant. Now can you tell me what should be the value of R2 in relation to R1? Obviously for these to oscillate, R2 should be equal to twice R1, and this circuit it contains 1, 2, 3, 4 resistors, 2 capacitors. You can make it out in the laboratory in 10 minutes, and you can see oscillations, beautiful sinusoidal oscillations. One op amp, you take a 741 and make connections R2 and R1. Now for starting oscillations, this must be remembered, exact, if you make exact R2 equal to 2 R1, it may not start the oscillations, because this is the condition for oscillation, that is a marginal condition. You should use slightly greater than 2 R1, so that the gain is slightly greater than 3. This is a practical trick. The gain has to be slightly greater than 3, then only the oscillation shall start. Now I showed you an op amp circuit. What about a BJT? Obviously if you use a BJT, you cannot do it a single stage. You shall require a 2-stage CE amplifier, and therefore you will require something like this: R sub C, C, R2, R1, second BJT, RE CE combination, and R sub C here plus VCC. Then you require the feedback circuit CR and a parallel C or parallel C and a resistance. Well, once again this resistance could be the second biasing resistance required here. You might use an extra resistance, or you may not use. Alright. Here however, the ideal conditions are not met. The input impedance of this amplifier is not infinity, it is R pi. Output impedance of this amplifier, what is the output impedance? What is the output impedance of this amplifier? It is R sub C approximately. It is R sub C, this one, and therefore the input impedance and the output impedance are not ideal. Therefore the frequency of oscillation shall not be 1 by RC. It would be modified. It would be modified to some other value. And this circuit for the oscillator is known as the Wien bridge circuit. The Wien bridge circuit. If one remembers, do you know what is a Wien bridge? No. Well, it is a very useful circuit for measurement of capacitors. What one does is a Wheatstone bridge, then an RC and a parallel RC. This is the unknown capacitor Cx, this is R, this is R, R1, R1. No, 2R1, well, let us call it R2 and R1, all right. The source is somewhere here and the detector is somewhere here. You of course know Wheatstone bridge, don't you? Yeah, okay. So, this is an AC bridge in which an unknown capacitor is to be measured. So, what one does is one uses an RC series and an RC parallel and then adjust this capacitor so as to obtain balance. And under balance condition you can show that Cx is equal to, the unknown capacitor is equal to the known capacitor, that is they are equal, provided R2 is equal to twice R1. Wien bridge circuit is a very popular circuit in many measurement techniques, measurement of non-electrical quantities by first converting to a capacitance and then measuring a capacitance. For example, you can measure mechanical displacement. What you do is you put a parallel plate capacitor, and if this is displaced, if this is loaded, then the distance decreases, so the capacitance increases, and that capacitance could be measured by the help of this circuit. Wien bridge is a very popular circuit for instrumentation. Next time we will, next time that means tomorrow, we will consider negative feedback and its effects.